Okay, hello everyone. Welcome back to the Intercontinental Seminar Series of Cosmology and Gravity. So today it's our big pleasure to have Dr. Kyriakos Destounis to give us a presentation. Kyriakos, he got his PhD in 2019 from CENTRA, Instituto Superior Técnico, IST, from the University of Lisbon. And then after that, he went to as a postdoc in University of Tübingen and also Sapienza University of Rome. And starting from this year, he will move back to IST as a junior researcher. So today he is going to talk about quasinormal modes and pseudospectra, a complementary notion to black hole spectroscopy. So without further ado, let me hand the stage to you, Kyriakos.
Very much. Thank you very much, Sergio. Thank you very much, everyone that is organizing this very interesting intercontinental seminar. Um, and yes, I will talk about quasi-normal modes, basically the spectrum of black holes and the pseudospectrum of black holes. This is a long story that lasted around 7 years because pseudospectra was supposed to be my topic of research in my PhD, but I failed to find the pseudospectrum of black holes, and we switched to something else, and things went very good because Vitor Cardoso has a lot of nice ideas. But after some years during COVID, a paper appeared by José Luis Jaramillo and Rodrigo Panoso Macedo and Lamy Salzaik. And since then, we started working again on pseudospectra in a very nice, complete setup. And I will try to explain to you what the pseudospectrum depicts, how it helps quasi-normal mode analysis and black hole spectroscopy. So as you can see down here, this talk will be based on various publications, which are big collaboration that we have together with Jaramillo, Macedo, Valentin Boyanov, Vitor Cardoso, and recently Paolo Pani and a student of us, Romeo Rosato. Okay, so I'm going to start with the most typical picture that anyone can show in such a discussion, which are black hole binaries and their evolution to form a steady, stable state. So, as we have seen now, and as we have seen more than 200 times by our detectors, LIGO, Virgo, and Kagra, the LVK collaboration, we can detect almost equal mass binaries with ground detectors that come from the in-spiral of two compact objects of similar mass that revolve around a common center of mass. And as they move in a gravitational field, they accelerate because they emit gravitational waves. And the gravitational wave emission, we can see here, the strain is very small, 10 to the minus 21. And here we show the numerical relativity filter that was used to match on the reconstructed template from the data. As the in-spiral moves, the objects come closer and closer together, and then they reach a very highly nonlinear regime, which is a merger of these two black holes, and this is the peak of radiation emitted. And afterwards, we see an exponential damping, which is called ringdown, which is the final object that is stabilizing itself in a stable ground state. And I will be mostly talking about this part of an in-spiral merge and ringdown waveform. Now, uh, there's an interesting connection because I use the word spectroscopy that a lot of people use these days to understand the parameters, the externally observable, the externally observed uh, quantities that a black hole has. And how we do it, we use black hole spectroscopy. Black hole spectroscopy is very similar to typical spectroscopy that we do with electromagnetic radiation. For example, we throw some light on a prism, and the prism, as Newton found many, many years ago, can break down the white light to its components, to all the electromagnetic spectrum, and we see them in different colors, from blue to red, or from, let's say, violet to uh, yeah, to dark red. So the same principle holds for black hole spectroscopy. We can take this final part, which is again the ring down, and we can try to fit this last part with a series of damped sinusoids that are connected with these quantities called quasinormal modes, QNMs. Now, we use damped sinusoids because this signal is decaying exponentially, and we use quasi-normal modes and not normal modes because the system is leaking energy. Okay, so the system, as it emits gravitational waves, some of them fall into the event horizon, some of them go away to infinity. Therefore, we're losing energy, and that's why we have a decay, and we don't have normal modes. Quasi-normal modes have the difference that instead of only having a normal, instead of having only a real part, sorry, they also have an imaginary part. So the real part is connected to the vibrational frequency of the quasi-normal mode, and the imaginary part to the decay timescale. So there's an infinite tower of these modes for any black hole system, and we can calculate them with many methods. And this is basically black hole spectroscopy, essentially the equivalent of the colors of the gravitational field instead of the electromagnetic spectrum. Now, at the time domain, so as time passes, we can recreate this ring down instead of using this very hard and very time-consuming numerical relativity evolutions of binaries. We can use quasi-circular black hole mergers, and by the Weil scalar, we can see again a ring down when these two black holes merge, and even much easier, an infalling particle. If we throw a particle inside the black hole, it will ring in a specific way. And after some point, the ring down does not depend on initial data, which means it does not depend on the properties of the infalling particle or the properties of the black holes before. So it's uniquely determined by the final mass, spin, electric field, and so on and so forth of the object that is formed. So what we can do, again, is avoid all the numerical relativity simulations to reach the ring down and use black hole perturbation theory, which is very, very useful, extremely useful for what the work we are doing in black hole spectroscopy. Here we can see a ring down signal of a Schwarzschild black hole when we throw an infalling particle with some Gaussian distribution, and this is in the linear scale, so you can see there is some damped sinusoid, but if we take the logarithm of this, actually the absolute value of the logarithm because they are negative values, then we see more information. And the information we obtain in the log-log scale is this initial part, which is the prompt part of the ring down that depends on the initial data, but after some point, when the exponential quasi-normal ringing starts, we have no dependence on initial data anymore. So all these ups and downs can be described by different quasi-normal modes that have been linearly combined together. The last part is the most interesting one that happens in asymptotically flat spacetimes, and our universe, even though it has a positive cosmological constant is very small. So what we expect to see is a tail. This is a price law cutoff. This is log. So in a linear scale, this corresponds to a polynomial. This is called the price law, and it occurs because of some mathematical subtleties of QNMs. So as we can see, quasi-normal modes cannot explain the whole signal. We cannot use an infinite tower of quasi-normal modes to explain the signal because there's a part that is independent of quasi-normal modes. But this has to do more with the mathematical aspect of completeness or incompleteness of the quasi-normal modes themselves. I would like to keep things cleaner for now and move on to the simplest task of using black hole perturbation, perturbation theory, and calculate quasi-normal modes. Now, all linear perturbations or first order perturbations to of either scalar type, such as the Klein-Gordon equation on a fixed background, or even electromagnetic and gravitational perturbations, so the Einstein equations at the linear level, end up to this wave equation. It's a box. Box is the derivative, the covariant derivative with the contravariant times the contravariant covariant derivative of phi, and phi here depends on all space-time coordinates, t, r, theta, and phi. So from this point on, I will be assuming always a line element that is static and spherically symmetric. So it will have this form, and if we use it and plug it into our wave equation, then we can get this very simple equation which has a second order derivative with respect to time, a second derivative with respect to our star, which is the tortoise coordinate defined here, pretty simple, plus an effective potential. And the effective potential has some specific form. For scalar electromagnetic and axial gravitational perturbations, it can be described like so. So S can be 0, 1, or 2, and it goes from scalar, electromagnetic, and axial gravitational. The polar gravitational perturbations in Schwarzschild and in other black holes, it's much more intricate, but it's there's an isospectrality that holds for Schwarzschild black holes. So calculating the axial part is equal to calculating the polar part. That's really found. This is the Reggie-Wheeler potential, for example. Now, this, as you can see, is an equation in the time domain because it has the time derivatives, and the field small phi still depends on time. So what do? We do a Fourier transform, and we write the equation in the frequency domain. We choose some harmonic time dependence, which gives rise to this omega here. And now we have a second derivative of our star, the tortoise coordinate, of only the radial part of the perturbation, plus omega squared minus the same effective potential times the same wave function equals 0. This is a master equation. This equation looks like a lot like Schrödinger's equation with an effective potential. And because of the format of the effective potential, to gain the quasi-normal mode spectrum, we need to give physically correct boundary conditions, or else we cannot solve it. And the physically appropriate ones are purely ingoing waves at the event horizon, RH, and purely outgoing waves at infinity. So nothing escapes the black hole horizon, and no new information comes from infinity. And this leads to the quasi-normal mode spectrum. Now, really quick, I can show you in the frequency domain how quasi-normal modes look. As now, I think you understand the infinite tower word, the phrase that I'm using. Here on the left, these are the Schwarzschild axial gravitational quasi-normal modes for angular quantum number L equals 2 and L equals 3 that comes from the spherical harmonics. You see some special points here. They call them algebraically special modes because they're purely imaginary, but we will not focus on them. And then here, all together, you can see the S equals 0, the scalar ones, for L equals 0 with blue. They do not intersect like the axial gravitational ones, which are with S equals 2 and L equals 2, and S equals 1 and L equals 1 are the electromagnetic. So these are really a lot of modes because every point here on this figure corresponds to a quasi-normal mode. So this is what we get usually when we have a ring down signal and we go from the time to the frequency domain by Fourier transform. We extract these quantities. To extract them with very high precision, of course, we need very precise numerical codes. We have plenty. There are plenty all over the place, even on the websites of Vitor Cardoso, Paolo Pani, Emanuele Berti, who they are experts in this field. You can find some routines on Mathematica, or even the modes themselves of the most typical Schwarzschild or Kerr black holes. Now, let's talk about the state of the art, because black hole spectroscopy is a whole program that is being built for the last decade and even more. So what we understand now clearly is that we can see the fundamental mode of the fundamental quasi-normal mode in ring down signals. So if we get the data from GW15, the first gravitational wave we observed, then we can safely extract the fundamental quasi-normal mode. The fundamental quasi-normal mode is the one with the smallest in absolute value imaginary part. It's the one that will decay last, and it's the most dominant one. It's the one that is louder. It has larger amplitude, or as they call it, excitation factors. But with only one quasi-normal mode, is really hard to do very precise recovery of the mass and the spin of the remnant. So we need to include overtones. It's mandatory. But there is an issue that is going on till now. And when I say till now, I mean yesterday there was a paper again about the overtone issue. It's amazing. So there's a group, let's call it the West Side group. It's from mostly from the States, from the United States, a group that includes Sol Tukolsky himself, where they insist that they find evidence of at least one overtone of the dominant angular mode L equals M equals 2 of a rotating black hole with 3.6 sigma confidence. They do this by creating numerical relativity waveforms and fitting the modes on the ring down part, but very close to the peak of the merger, which may produce some errors because this is a very nonlinear regime. And this is where the European side started working on, and they realized, or at least that's what they claim, is that there's no evidence whatsoever of an overtone in the data because they are fitted at the waveform peak, and the time that we start the fitting on the ring down is very, very, very important. So the overtone detection can easily be noise dominated. They actually have done this group of Vitor Cardoso, Roberto Cotesta, Gregorio Carullo, Emanuele Berti, a guy from the United States. They have found that if you inject noise in gravitational wave data, we can actually see this as a overtone. It makes you think that it's an overtone, but it's practically noise. So that's why I have these question marks here, because this is an ongoing academic battle, but it's not a battle. I mean, they're just trying to find the most consistent way to 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 set up the best black hole spectroscopy program ever. Okay, so I mean, everybody needs to agree at some point. But during this analysis of overtones and all this chaos with these PRDs and PRLs back and forth, um, these groups also separately found the existence of nonlinear quasi-normal modes. And of course, those were expected because they found them close to the peak of the merger, the peak of the amplitude of the ringdown. So that's why I say that time, the time that we start the fit is very important. And when we start very close to the merger, which is a highly nonlinear regime, we expect mode mixing. We expect the quasi-normal modes on first order to source second order quasi-normal modes, and so on and so forth. And this indeed happens. They call them quadratic QNMs. And both teams, at least here, agree that they exist. And actually, in this paper that appeared just yesterday, they use both nonlinearities, and they still can find an overtone because nonlinearities do not play a dominant role at the fitting process. Now, again, we are waiting to see how this will go, but we are in a really nice path. But a new thing appeared with this, which is connected to the pseudospectrum around 2020. It got published in 2021 here by Jaramillo and Macedo and Lamis Alsaik, which is the stability of the quasi-normal modes, let's say, under small fluctuations. Think of it as the quasi-normal modes of quasi-normal modes. It's a little bit confusing, but this is a question that started very early, back in the days, in the 90s, from Hans-Peter Nollert. And very recently, we understood what he found back then. This is what Professor Nollert tried to do in 1996. He was still working in Tübingen, and he didn't care that much about black hole spectroscopy or anything like that. What he cared about was to form a complete basis of quasi-normal modes. So he wanted to find a way to avoid the branch cut systematically so that he can create a set of quasi-normal modes that form a complete basis of functions, because in principle they do not. So his idea was very straightforward. Instead of using the smooth potential that we see here, which is the Schwarzschild potential, he included steps. So he made a piecewise discretization to the potential. Now, of course, when we cut at some point that is not exactly infinity, we avoid the branch cut. And this leads to the formation of a complete set of quasi-normal modes that can explain the ring down. But to his great surprise, and to the surprise of everybody, the spectrum changed completely. So he had a ring down signal that was the same as the continuous line, put as many steps as you want, and as he was increasing the number of steps, he was seeing a divergence of the QNMs from the actual Schwarzschild QNMs. And we can see them down here. The Schwarzschild QNMs are these asterisks. This is the fundamental mode, this is the first overtone, and they go up and they do this, as we saw them before in the infinite tower. And as he was increasing the steps, He was seeing a logarithmic branch forming and going downwards to the real axis. So what is this and why it happens? He didn't know. It took more than 20 years to understand what is happening here, but this phenomenon now is dubbed spectral instability. So if you perturb in any sense your continuous effective potential of the black hole, you will get this sort of branches instead of some small deviation around the quasi-normal mode of the continuous uh, black hole potential, which is very weird because this essentially gives a very strong sensitivity to where a quasi-normal mode can be in the complex plane if you slightly perturb the potential. It's a very confusing thing that happens, but I will try to explain through the pseudospectrum, which is this mathematical notion that is not new. It has been used in quantum mechanics, chemistry, hydrodynamics, and it has been found very useful. And Jaramillo and his collaborators first used it to understand why these lines appear, these logarithmic uh, complex plane points, which were the new QNMs, the perturbed QNMs. So uh, essentially, this is like perturbing the environment of the black hole. Assume that you have a effective potential and you had a very high frequency perturbation, like sort of quantum effect close to the horizon, or you add a bump that corresponds to some thin disk around the black hole of matter. And what they found is a drastically altered quasi-normal spectrum also, Jaramillo, and then later Mark together with me and some other collaborators. Now, how do we understand, how do we know that we have a spectral instability? Because I just showed you a figure. I didn't quantify it. Now, this is how we quantify it. If the quasi-normal mode migration, when we perturb the potential, uh, is disproportional to the perturbation scale, then the system exhibits a spectral instability. This is in the book of Trefeth and Embry, which are the masters of pseudospectra, not black holes, any kind of system. They use it. And this is what they call spectral instability. So imagine that you perturb the potential with a small bump of order 10 to the minus 6. Do you see migration of order 10 to the minus 6? Then you do not have a spectral instability. Do you see migration that is much larger than 10 to the minus 6 in the complex plane? Then you have a spectral instability. And this is how we quantify things. So these spectral instabilities, I want to stress that are not instabilities of the spacetime. They are instabilities or sensitivity of the spectrum. It moves around the complex plane very easily, but this doesn't mean that the spacetime is destabilized. The spacetime stays stable, okay, modally stable. So these quasi-normal stabilities have important implications to understand gravitational wave detections, because we can get confused with the modes that we are seeing in a ringdown signal and assume that it might be a different object, a modified theory of gravity, but what happened is just a tiny astrophysical environment, or, I mean, all the objects we know live in astrophysical environments, even supermassive black holes at the center of galaxies. So they should exhibit these spectral instabilities. And the pseudospectrum is able to capture exactly spectral instabilities. What it describes is a topographic map of spectral migration in the complex plane, as I explained before. So it gives you a map in the complex plane and tells you where the mode would go if we assume this sort of perturbation. So its definition in the end is connected to how close a point in the complex plane is to an eigenvalue, a spectral point. So this notion of closeness is another really hard topic, but it is set. I don't want to discuss it a lot. We can discuss it later, but it has to do on how you measure this closeness. And here is why we need to know how to measure this closeness, because we take norms of operators or matrices. But the purely mathematical definition of the pseudospectrum, which we call sigma epsilon of A, capital A, where capital A is, for example, a matrix that describes the master equation with the boundary conditions imposed. And then there are two definitions that I like to discuss. The first one basically says, without all that, that if we have a perturbation of the master equation operator, the wave equation operator, that is smaller than epsilon, then the new complex plane eigenvalues Z will belong to the spectrum of A plus delta A. So this is the definition of the spectrum. We add the small perturbation to the matrix that describes wave propagation, and we find a new spectrum. And this belongs to this epsilon pseudospectrum. Then we change epsilon, we make it larger, smaller, or whatever, and we find different contours, different contour lines of spectral migration. But mechanically, to calculate this, there's a very beautiful question that we can ask, which is which connects with the robustness of the question of an eigenvalue. Think about eigenvalues. What do we ask? We ask if this quantity without the to the minus one, essentially, the determinant is equal to 0. We may be extremely close to an eigenvalue of a matrix. We can be 10 to the minus 50, but it's not 0. Okay, so the answer to the determinant of this z minus a would not be 0. But in principle, we're very close to the eigenvalue. If we inverse this question, we make the question more robust. This capital R, I forgot this L is A, actually, is called the resolvent operator or the resolvent matrix. And it is defined like so. Z is a complex plane point. A is, for us, the wave equation operator or wave equation matrix, and it doesn't ask uh, if we are exactly at 0, but it asks the inverse thing. So if how close we are to a spectral point. So how larger is this than 1 over epsilon, where epsilon is very small. And again, we can choose different epsilon and create different contour lines. In a three-dimensional depiction, we see the imaginary part of Z, the real part of Z. This is the complex plane, and we see a three-dimensional surface with some very very sharp cones. These sharp cones, according to the z-axis, correspond to the norm of the resolvent. The question is the following. If we are at this point, we are very close to the sharp point, but we're not close to the eigenvalue. But this information is important. The same happens if we are here. We are close and we have some norm that is elevated more than usual. So not only the pseudospectrum tells you if you are close to quasinormal modes, which is very nicely set, it also tells you if you are close to a pseudo-resonance, a resonance that wouldn't form a peak that goes to infinity, but would form a small bump in the three-dimensional phase space. So far, things have become a little bit more mathy, but I can simplify things with these two figures, which I describe spectral stability and spectral instability. So here, the wave equation has a potential that is not the Reggie-Wheeler, but it's the Postel-Teller. It's a much simpler potential that decays exponentially on both sides. There are no branch cuts, the ring down is clean, and you can use the infinite tower of quasi-normal modes to represent the ring down signal. Quasi-normal modes, they are eigenvalues of the system with a positive Teller potential. Now, let's start from the left-hand side, spectral stability, which is very important. When we kill dissipation from our operator, what do we have? We have a closed system. We have a system that exhibits normal modes, something like the potential well in quantum mechanics, for example. At this stage, which we by hand take out dissipation, what I mean by dissipation is we take out the purely outgoing waves at infinity and the purely ingoing waves at the event horizon. So we have a closed system. Then we just have normal modes bouncing back and forth. And that's why these red dots, which correspond to the normal modes of this operator, are real. They have no imaginary part. What do we see? We see, as we call, a flat pseudospectrum. This is the pseudospectrum, and the white part are the pseudospectral contour lines, different epsilon. Okay, it's most significant to see the zoom in, because when we have spectral stability around the normal modes or the eigenvalues of the matrix, we see concentric circles that are forming, and they have a radius of epsilon. So we apply a perturbation of 10 to the minus 1, and we will go in a distance of 10 to the minus 1 and not further inside the circle. That's a clear-cut example of spectral stability. Flat pseudospectrum and concentric circles of radius epsilon. On the other hand, see what happens when we have a spectral instability. Let's choose one of these numbers here. I'm gonna choose 10 to the minus 15 because this is in log scale, and 10 to the minus 15 is the epsilon that we choose, which corresponds somewhere in this line, let's say in these two modes. Now, we see that we have a contour line right underneath them, which tells us that if we add the perturbation of 10 to the minus 15 or smaller, or larger, no, or smaller, then these two QNMs and the other overtones can travel inside this huge box, which is practically infinite, in the complex plane. If we increase the strength of the perturbation, go to the 10 to the minus 3, for example, we can even reach the fundamental mode, and anything that lies above the fundamental mode can be a new perturbed QNM. So these red dots, which are the eigenvalues, can spread all over this place. Okay, so you see now what Nollard found. Nollard found the pseudospectral contour lines. He was perturbing the potential and he was getting a new spectrum. The new spectrum was falling on the maximal spectral migration, on the branches. That's why we call those Nollard branches. It's really brilliant. It took 25 years to reach this conclusion, but it puts together really nicely the two problems. Now, of course, we need to justify that this happens also in black holes, and with more realistic, let's say, perturbations, because the piecewise perturbations are very rough and they do not have compact support. So what Jaramillo and the rest did is that they perturbed only the potential part with a small perturbation of a sinusoid, with k a frequency and some norm. And the norm was very small, they kept it 10 to the minus 8. For k equals 1, these open boxes and stay around exactly all the quasi-normal modes of a Schwarzschild black hole. So if you add a perturbation with a very small frequency, nothing happens. Okay, but if you increase the frequency, then you see them branching out. And they are branching out in a manner that falls almost on top on the pseudospectral contour lines. So indeed, what Nollard found is that adding something very small in any way, piecewise, or here with compact support, like a sinusoid function with some norm and some frequency, you can get back these branches. What what we have here till now? We have seen that perturbations to the effective potential can give us spectral migration in the complex plane of overtones. See how the branches reach till down here for 10 to the minus 4 norm and 20 frequency, but down here, which we have the fundamental mode of a Schwarzschild black hole, we don't see any branch. Any perturbation we add to it, it stays down here. It doesn't move. So Jaramillo in the beginning thought that the fundamental mode cannot be destabilized with realistic perturbations. And we will discuss this later because the fundamental mode is the most important mode for ringdown analysis and black hole spectroscopy. And of course the overtones also, if we believe in them, if we believe that they exist. This is the pseudospectrum of Rising-Nordstrom black holes. This is the gravitoelectric part, specifically, that we calculated with Vitor Cardoso, Emanuele Berti, Rodrigo Panoso Macedo, and Jose Luis Jaramillo. And you see, again, these Nollard branches. Now, I have differentiated these two different colors. The red ones are quasi-normal modes. The blue ones are non-convergent modes that appear due to the code that we are using. We use a specific code that includes infinity into the operator, and it gives us these non-convergent modes. But we have ultimate control of them because we can increase the discretization of the matrix and we can increase our accuracy, and we see that these modes move around a lot, but this one, the red ones, stay in the same place and they just converge to a value. These ones, therefore the blue ones, are non-convergent. We found the pseudospectrum of de Sitter black holes very recently with Rodrigo Macedo and Valentin Boyanov, a postdoc at CENTRA. And the beautiful thing is that any red dot you see here is a quasi-normal mode. Even the imaginary ones, the imaginary parts here and here, for some different, this is for L equals 2, this is for L equals 1, and different cosmological constants, because this is a Schwarzschild black hole, we see that we also have purely imaginary modes. These purely imaginary modes are nothing but the cosmological horizon modes, as they call them in the literature, or the de Sitter modes, because they appear when the asymptotic is de Sitter and not asymptotically flat. And these are actual QNMs, not QNMs because they only decay, but still they are true part of the spectrum. They converge. So this is a very clean example of spectral instability without the contamination of these non-convergent branch cut modes, as we call them. This is what made us certain together, of course, with a Pseudospectra potential, that everything works well with our numerics. We found the pseudospectrum of anti-de Sitter black holes. This is a Schwarzschild anti-de Sitter with a horizon much larger than the ADS radius. Again, we put perturbations, we see that they fall on the branches, but here something special happens. And this happens because of a mathematical theorem that I don't want to go into deep detail, but it essentially tells us that in the complex plane, after below some point, the pseudospectrum starts showing aspects of spectral stability. Even though we have a black hole that is an ADS black hole, so at infinity it reflects waves back, but the event horizon absorbs these waves, so we still have a leaky system, we still have dissipation. We can find some part of the complex plane where this beautiful thing happens. We have a mode, which is this one down here, and we have zoomed and we see concentric circles around it. So this is something, again, that was shocking to us, but it agrees with math. The same thing happens in the sitter. Actually, Warnick, the guy that did the proof, the mathematical proof, did it recently for the sitter also. But the interest is not towards there, but it's more in astrophysical, the astrophysical point. So we didn't look too hard, but this was a very interesting example. Now, as I said, we have not found a way to destabilize the fundamental mode, to make it move around the spectrum very in large distances. But at 2022, with Mark Cheung, Emanuele Berti, Rodrigo, and Vitor, we found that if we add a small perturbation, a tiny bump, some distance a away from the Pseudospectra, from the Reggie-Wheeler potential, even if this is a Pseudospectra bump or a Gaussian bump, then we can actually see the destabilization of the fundamental mode. And this agrees perfectly with the pseudospectrum, because the pseudospectrum tells us that the branches open from the fundamental mode and up if we increase the strength, the scale of the perturbation. And this is how things happen. We start with this black dot, which is the original fundamental mode, and we increase the distance between the two bumps. These are not to scale, this is much smaller, and you see that initially we have a spiral movement, and then an overtone takes over, a second overtone, third overtone takes over, and then we have a huge jump. And the new fundamental mode is a long-lived mode that is trapped between these two bumps, essentially. And that's what we see here. We see the spiral, and at some point, we jump to an overtone, we go down, we jump to another overtone, down, jump to another overtone, and then we have a huge jump of order 10 to the minus 1. We have included the Pseudospectra potential with 10 to the minus 6 height, amplitude, and we get a destabilization, like we get a migration of the fundamental mode in the complex plane of order 10 to the minus 2. This is a spectral instability. We see it here also. We have this quasi-stable state, then first overtone becomes a fundamental, the second, the third, and then this huge jump in the destabilized region. And these are a couple of phase diagrams, but I need to start wrapping things up. And I would like to discuss this new thing that we are trying to do, which is to circumvent spectral instabilities, because if they exist, we will have problems in black hole spectroscopy if they exist in the ringdown. And in principle, at least at the frequency domain, we see them. So how can we avoid them? We need to find stable observables with the quasi-normal modes that are spectrally unstable, but somehow conspire to give us a stable observable. And we can use this as an alternative method to black hole spectroscopy to fortify black hole spectroscopy with other methodologies so that we are sure that we're doing the right thing. And recently, this has been done with the gray body factors. So the gray body factors were used to fit a ringdown signal in the frequency domain. And these people, Osita, and Okobayashi with Osita again, managed to do parameter estimation, managed to fit the gray body factor, which is a continuous function, to a ringdown and extract correctly the parameters of the final object, which is very interesting. Therefore, the gray body factors may be this complementary route to ringdown analysis. They do not have overtones because they're continuous functions, so they evade all this dispute with overtones, and they do not suffer from spectral instabilities or the continuous analog of spectral instabilities. As we showed in the next slide, the gray body factors are stable. So the gray body factors, really quick, characterize the deviation of the emission of spectrum of a black hole from a pure black hole body. Okay, so some radiation comes out through Hawking radiation from the event horizon, and particles are gravitationally attracted back. They fall back in, the spectrum changes, and an asymptotic observer doesn't see the black body spectrum of the black hole, but he sees something else. So how we find them? Scattering computation. So you see the wave equation as before, but now we put a source because here is an infalling particle. And the gray body factors capital gamma are essentially the reflection coefficients. So these are the boundary conditions now. We have purely ingoing waves at the event horizon, but we have the two solutions of the wave equation at infinity, which are ingoing and outgoing. And from this capital A in and out, which are the excitation factors, we can find the reflectivity and transmittivity coefficients. And this gamma is essentially the gray body factor, this quantity here. Now, this is with respect to omega. We want to take it to the time domain. So we take a Fourier transform of this quantity, and we go to the time domain, and then we try to reproduce a ring-down signal. First of all, we see that in QNMs we have a spectral instability, as I showed before, but for gray body factors, you see that we are using this quantity here, which is an integral of the perturbed gray body factor minus the unperturbed gray body factor, and normalized by it. And we see that it mostly stays stable and below the scale of the perturbation. So we see here that the gray body factors have this amazing property of remaining stable no matter what. This bump here is just something that happens close to the event horizon at the light ring. And because gray body factors are a local effect, that's why this happens here. But it doesn't go above epsilon, or if it goes just a little bit. But mostly they are flat like this, and therefore we have stability here. We have a stable observable. And finally, we put all this thing together. We reconstruct the ring down signal with perturbed QNMs, which are spectrally unstable, by using the gray body factors. As I said before, we take the reflectivity coefficient, we take a Fourier transform, we use some complex analysis to find the simple poles close to the quasi-normal modes. This is the residual theorem, essentially. And we have used a time domain analysis, this signal, this black one or dark blue. And then we have used 7 unperturbed QNMs, and we get this fit, the dust orange. And then when we use perturbed QNMs, just the fundamental one, we get something like this. And when we use 3 perturbed QNMs, or 2, I think is 0, yeah, 0, 1, 2, 3, then we see a much better fit. It's the dust red, much better fit than even the 7 unperturbed QNMs. We have calculated the mismatch. It's not the best, but the one for the perturbed QNMs is better than the 7 are perturbed. So we start from a spectrally stable quantity, and with the help of spectrally unstable QNMs, we can recreate a ringdown, which is very important because here we can combine this knowledge to extract correctly the mass and spin of a black hole. This is Farzel, by the way, with a bump, but either way, with just some perturbed QNMs or some unperturbed QNMs. You choose how you want to do it. And here I will just stop talking and I will show you the conclusions and future prospects. Thank you very much.
Thank you very much, Kyriakos, for a nice talk. Any questions from the audience? So, Kyriakos, I have a question. So, is it true that when we want to destroy the fundamental mode frequency, is it true that we really need to have an additional bump in the effective potential?
Yes, this was one of the ways that we found that destabilizes the fundamental mode. Yes.
Yes. So can I understand in the way that, like, when you have an effect, when you have an additional bump, then in principle you are going to have an echo in the time domain, right? So
Exactly.
is
And
it the
that's
reason that precisely destroy the fundamental mode?
exactly. The further we take the bump, the longer it takes for the echo to appear. So the more long-lived it becomes because it's a trap mode and it lives in a cavity and it creates these echoes. So at the ring down level, we would see
I see.
repetitions of the ring down. Yeah.
Okay. Thank you. Any other questions? Maybe I can have one more, if no one.
No problem.
So, how about like when you go to higher multiple number modes, like when you increase the value of L, and in principle you are going to match or correspond to the quantities in the spherical photon orbits around the black holes. So, does it also have this kind of spectral instability for those high multiple number modes?
Yes, they do. And this is a nice assist for me to show you this figure. Okay, we discussed the echoes. As you know, there is a bump for a black hole only. It gives us this ring down signal. When we have a wormhole or a star-like exotic compact object that creates these trapping regions, then we can have these repetitions called echoes. Okay, now this is the pseudospectrum of an exotic compact object that we have put on the surface, close to the, put a surface that is perfectly reflective in close to the would-be horizon, very close, like 10 to the minus 3, 10 to the minus 4 distance from it. This is the L equal to gravitational perturbations, where we still see spectral instability, and actually we see some of the contour lines crossing on the side where unstable eigenvalues reside. And this is for L equals 2. This is for L equals 10. For L equals 10, things are even worse in this case. Worse in the sense that this object at the linear level looks stable. It has the long-lived modes that produce the echoes on the ring down. But if we take higher order effects if we take second order perturbations, for example, then it becomes unstable. And it becomes unstable precisely because the contour lines cross to the complex plane part where instability, actual instability of spacetime happens, modal instability. And this has been proven in another paper by Keir, and it actually says that the larger L is, the more prone to instability the compact object is.
I see. Thank you very much.
Thank you too.
Any other questions?
Yes, sir.
If there's no question, then maybe we can stop recording. Please, Kostas.